Swayam Prabha. Digital India. Educated India.
Next comes conditional probability. Now I start with an example. Suppose in a lot of 100 shirts, there are 80 non-defective and 20 defective shirts. So you have a lot of 100 shirts, 80 non-defective and 20 defective. So out of 100, defective and non-defective. Defective is 20 and non-defective is 80. Total is 100. The event we are describing, the first shirt is defective. I pick up a shirt, we choose two shirts from the lot with replacement and without replacement. And two shirts are chosen, one after the other. A, the event is the first shirt is defective. So the event described as the first pick is going to be defective. And B, the second shirt or the second pick is also going to be defective. Now, what are the values of PA and PB? If this is the questions, the answer is simple. When I am going with replacement, that is, after picking up, I put the shirt back again and mix with the lot. So with replacement, PA is going to be 20 by 100 because I have 20 defective shirts out of 100. So the answer is simple, 20 by 100, 1 upon 5. And if I replace it back, then PB, second shirt will be defective, again will be 20 by 100, that is equal to 1 upon 5. So PA and PB, individually the values are 1 upon 5, 1 upon 5 when it is done with replacement. If I don't replace it back, after I draw the first shirt and whatever happened, I keep it and then go for the second, but I don't put it back into the stack again. So without replacement, if we go, then the first shirt is defective, there is no change, PA is going to be 1 upon 5. But what is going to be the PB? Second shirt is defective, there is a question mark here. Because what will happen to PB depends what has happened in the first draw. So this answer depends on what has happened earlier. We need to know the composition of the lot at the time of second items chosen. Earlier the composition was out of 100, 80 non-defective, 20 defective. After the first shirt has been drawn, so now we have one shirt less. We are not replacing it back. So number of shirt left is one shirt less. But that one shirt, is it coming from defective or non-defective? So everything will depend what has happened earlier. So probability of occurring the event B, given that event A has occurred, is represented by P B by A. That is how we write it. P, probability of event B given A has occurred. And this is what is known as conditional probability. So P B by A is going to be, in this case, 19 by 99, because number of shots has reduced from 100 to 99. And if the previous one is defective, so number of defective left is 19 now. So PB by A is going to be 19 by 99. So that is the from the experiment, from the example, we see that in some cases the probability of an event depends on what has happened earlier. So this is known as conditional probability. So conditional probability of A given B is written as PA by B, and this is, by formula we can write it PA intersection B by PB. This also can be proved. Or conditional probability of B given A, we write it P slash A. The numerator remains same, PA intersection B by PA. So this formula one has to remember how to write it. P of A given B or P of B given A is written as like this, where the numerator in both the cases remains same, the denominator changes. So P probability of A given B, so PB will come at the bottom or the denominator. Similarly, PB given A, P of A will come in the denominator. This is how you should remember. So PA oblique B or P oblique B are not same. These values may not be same also. So this should not be confused that PA oblique B and PB oblique A are same. They are not same. So we can see some experiment, will also solve some problems and see that the probabilities could be different. Now comes mutually exclusive and independent events. I've already discussed earlier that mutually exclusive events, and we'll now discuss about the independent events also. Mutually exclusive events is events A and B cannot occur simultaneously. That is mutually exclusive. That means PA intersection, when mathematically, is a null set. Null, that is shy. Write it like this. PA intersection B is basically 0, because this is something which is impossible, because they are mutually exclusive. If I toss a dice, I cannot see 2 and 4 simultaneously. The face would be either 2 or 4 or 3 or 5. So one of the 6 faces will appear. So this, then we say this is mutually exclusive. And PA given B in this case is going to be 0. If the two events are mutually exclusive, their intersection is going to be 0, and their conditional probability given P of A given B or PB given A is also going to be 0, because these two are not together. And independent events, two events A and B are independent, mathematically means PA by B is PA and PB by A is going to be PB. If they are independent, then given B has occurred, what is the probability of A? Will be always PA, because the occurrence of B cannot influence the occurrence of A. So PA given B is PA, PB given A is also PB. That means given A has occurred, the probability of B happening will be PB, because the event A, occurrence of event A has no consequence on the occurrence of event B. Then only they are called mutually independent events. And when we write them mathematically, then we write this way, that PA given B is PA, or PB given A is PB. So multiplication rule for the independent events will be PA intersection B is PA into PB, because the two events are independent. Like suppose I say I toss a coin twice. What is the probability that I will get head in both the tosses? So event 1 is getting head in the first toss. The value is half. Event 2 is getting head in the second toss. The value is also half. So probability of getting head in both the tosses will be half into half. That is 1 upon 4. Because the two events are independent of each other. What has happened in the previous toss does not influence what is going to happen in the next tossing. Another example, if A and B are mutually exclusive events, and PA is given 0.26, PB is 0.45, find what is PA bar, PA union B, PA intersection, complement of B, and P of complement of A and B together. That is the intersection part. Mutually exclusive event, so we represent them like this, the way it is shown here. The solution, first of all, PA complement is going to be 1 minus PA. So 1 minus 0.26, PA is given, so the value is 0.74. PA union B will be how much? This is the formula, PA plus PB minus PA intersection B. In the present case, PA, PB values are given. PA intersection B, this value is how much? This value is going to be 0, because they are mutually exclusive. And thus, the result is 0.71. Since PA intersection B is a null set, because there is no common area, because they are mutually exclusive. PA intersection complement of B is going to be PA into PB complement. This value is going to be 0.26. You will try to understand how it is coming 0.26, and PA complement, B complement, their intersections. So A complement and B complement intersection means the area outside A and B. Basically this is, if you look at this diagram, because they are mutually exclusive event, so PA complement means the area outside A, PB complement means the area outside B. So whatever area of this rectangle I find, excluding A and B, that area is basically PA intersection, A complement intersection B complement. This will be 1 minus PA union B. So 1 minus PA union B, we have found out 0.71. This is going to be 0.29. So this is how we can find out the probabilities Another example we are taking. Let A and B, two events associated with an experiment. PA value is given, PA union B is given, and PB is unknown, that is just small p. Now the question is, for what choice of small p are A and B mutually exclusive? And for what choice of p are A and B independent? This is what we have to find out. So mutually exclusive events is represented by this diagram. Now the solution, first case, events A and B are mutually exclusive. So PA intersection B is going to be basically 0. There is no common area between them. That means PA union B, PA plus PB minus PA intersection B is formula we know. In this formula, we substitute the values. A union B is given 0.7, PA is 0.4, PB is P, PA intersection B is 0. So this is the equation. We find out what is the value of P, 0.3. So if the value of PB is 0.3, then only A and B will be mutually exclusive. The other question is, for what choice of P, A and B are independent? Say this diagram is shown A and B. If they are independent, that means PA intersection B will be PA into PB. So using the same PA union B formula, this is what we know: PA plus PB, PA intersection B. What is going to be the value of P intersection B? If it is given independent, it is going to be PA into PB. So we now substitute the values of PA, PB in this. 0.7 is going to 0.4 plus small p minus 0.4 p. From there, we can find out what is the value of small p is coming 0.5. So if the value of small p, that is PB, is 0.5, then only A and B are independent events. This is how we can calculate. So one has to solve many problems. We have to get a book on probability theories, and then you have to solve many problems. There are many examples which will be there, and there will be many numericals also. So the more you solve, the more you'll be able to learn. So you have to practice a lot. Obviously, in the lecture class, we cannot solve too many problems. So now we'll come to general multiplication rule. If two events A and B are such that they occur together, the probability of A will occur given B has already occurred is PA intersection B, PA, P, B given A, if PA is not equal to 0. So A intersection B is PA into P, B given A. Or I can write this is PB into PA given B. Actually, this is coming from the conditional probability. We have already learned earlier PA given B, and from there, if we find out what is PA intersection B, then we can easily write. So we wrote earlier, if you remember, go back to the slides, then we'll find We have different conditional probabilities. P A given B is P A intersection B by PB. That basically means P intersection B is going to be the multiplication of these two. That's what we have written it here. This is known as general multiplication rule. And we can give an example. Again, suppose garments are made up by sewing together 4 pieces of fabrics, 2 type A and 2 type B. So type A 2 pieces, type B 2 pieces, and then they are being joined to make some garment. The proportion of pieces of type A that contains holes is 2%. The proportion of pieces type B that contains hole is 3%. That means some fabrics are defective and there are holes in there. And generally 2% of type A having holes and 3% of those pieces which will be joined, they are having holes. A garment is scrapped if it contains 2 or more pieces with holes. If pieces are selected at random for making up, calculate the proportion of scrapped garments. How many garments will be finally rejected? If we get 2 or more pieces with holes, then we reject the garments. 2 or more pieces with holes. So there are 4 pieces in a garment. Only 1 piece having hole, we will accept it. But if it is 2 pieces having hole, we will reject. 3 pieces having holes, also reject. 4 pieces having holes, also will be rejected. So as long as out of the 4 pieces, only 1 piece is having hole, the garment will be accepted. Now the question that is being asked is proportion of scrapped garments, the rejected garments. So selection possibilities for acceptable garments. If I write A type of fabric, B type of fabric piece. So events are here E1, E2, E3, E4, E5. And let's say I take 2 pieces A1, A2, B 2 pieces B1, B2. So what are the outcomes? Outcomes could be all are good, G, 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 G. G stands for good pieces. Or it could be event E2, A1 piece is defective, rest are good. Or the other is E3, A2 is defective, rest are good. E4 is A type fabric are good. In the case of B, B1 is not good, but B2 is fine. Or it could be these 3 are good, this one is defective. So these are the various possibilities which are there. So PA is 0.02, PB is 0.03. While selecting 4 pieces, 2 from A and 2 from B, we write them as A1, A2 or B1, B2. Probability of the event that all are good pieces will be how much? Everything, all of them are good. That means this event. So first A1 has to be good, second also has to be good, third has to be good, fourth has to be good. So we can write this to be 1 minus PA, 1 minus PA. This is for A1, this is for A2. Probabilities are same because they are coming from the same source, same A type of fabric. This is 1 minus PB, this is 1 minus PB. But PA and PB represents the probability of having holes. So 1 minus PA is probability of not having holes, that is not being defective. So all these selections will be consecutively good Means I have to multiply probability of A1 not defective into probability of A2 not being defective into probability of B1 not being defective and probability of B2 not being defective. This probability will be multiplication, and this value, if we put those values, we'll get a figure 0.9036. That will be the answer. That all are good pieces. Now comes probability of event 2. That out of 2 pieces of A, 1 piece will be defective and both pieces of B will be good. That means E2 and E3. So what is this thing? Well, I can write this E2 is how much? 1 minus PA. So this is defective. A1. A1 not defective, sorry. So it will be 1 minus PA. Then this one is defective. One of them is defective into PA, and the rest two are not defective. 1 minus PB into 1 minus PB. So if I put the values, this will give you a figure, this 0.0184. And probability, similarly, probability of event E3 also we have found out, because we need to know, as long as there is one defective out of 4, it will be accepted as not having any defects in the garment. So we have to know the event probabilities of event E1, E2, E3, E4, E5. So for E2 and E3, the values will be exactly same. So it will be 0.01, same value. Then you go to the next page. Probability of E4 and E5 will also be similar, because here one of B type of fabric will be defective. So first two are good. So it should be E4 will be what? 1 minus PA, 1 minus P. A type being good here, A type being good, and one of the B type is being good. This is B being defective. So these are the corresponding probabilities. The value is coming 0.028. For E5, exactly will be same, 12.028. That means probability that the makeup will not be scrapped, it will be accepted, is sum of all those probabilities, P1, P2, P3, P4, P5. And if we add them, all these figures, we get a figure 0.9964. So that is the probability of acceptance. Almost 99.6% of the garments will be accepted. So when you go for 10,000 pieces, or 10 lakh pieces or 1 lakh pieces, we can say, okay, how many of them are going to be rejected. We can get some idea. So probability that will be scrapped is going to be, therefore, this is the acceptance probability. So rejection probability will be 1 minus of this. So this figure is going to be 0.36%. So closely 0.4. So 0.4% of the garment is going to be rejected. So out of 100, 0.4 will be rejected, or 0.36 to be very exact. Then you can multiply out of 100 so much. So out of 1,000 how many? Out of 10,000 how many? Out of 1 lakh pieces how many? And therefore what could be the loss? That also we can calculate. One more example now. So go through these solutions very carefully, try to understand each and every step, and then you must practice also. A room contains 3 machines, A, B, and C. The probability that A will stop during a certain day is 3 by 4, that is 0.75. Probability that B will stop is half. Probability that C will stop is 1/3. Suppose you have 3 machines are there in a room, maybe 3 knitting machines or 3 sewing machines or whatever 3 machines are there. Calculate the respective probabilities that 0, 1, 2, 3 machines will stop during the day. In the whole day, 0 stoppage. All the machines worked. 1 stoppage. 1 machine did not work, or 2, or maximum 3, because 3 is the maximum number of machines. So outcomes could be either 0 or 1 or 2 or 3. And we have to find out the respective probabilities. And what is the most probable number of stopped machines? So find out these solutions. So probability of stoppages are given for individual machines. PA, PB and PC. Obviously, these 3 machine stoppages are independent of each other. Stoppages of B has nothing to do with the stoppages of A or C. They are running independently and they are not anyway dependent on each other. So the events are therefore independent in nature. So what is PA complement? That it will not stop. Complement means it will not stop. 1 minus 3 by 4, 1 upon 4. PB complement is half. PC complement is 1 up minus 1 upon 3, 2 by 3. Machine stoppages are independent events. Stoppage of the one machine is not influenced by the stoppage of the other machines, because they are not really interconnected by any way. Therefore, the probability of the stoppage, if we write it by PS, then stoppage probability is PS is going to be PA bar, that is S is going to be 0, that is stoppage will be 0, that means it will work. PA bar, that is PA complement into PB complement to PC complement. We multiply them, we get a figure 1 upon 12. So PS equal to 0, this figure is half. PS to be 1, we have given this value. It is this plus this plus this. That is either C is stopping, the rest two are not stopping, or A is stopping, BC is not stopping, or B is stopping, A and C are not stopping. So it is the summation of this probability, this plus this plus this. 3 individual probabilities to be added together, and therefore this is the formula we use, and we substitute the values and we get the figure 9 upon 24, that one machine will stop. Following similar procedure, we can find out PS will be S equal to 2 and PS equal to 3. The 3 machines, all of them will stop, is 1 upon 8. So PS 0, 1, 2 all have been calculated, and the highest value, the most probable number of stop machine is which value? PS0 is 2 by 24, PS1 is 9 by 24, PS2 equal to 5 by 12, that is 10 by 24, PS3 equal to 1 upon 8, that means 1 upon, that means it will be not 1, it will be 3 upon 24. We are multiplying, we are keeping the denominator exactly same. So 1 upon 8 basically means 3 upon 24. So therefore, out of this, if we compare which one is maximum, probability is maximum in which case? In this case, it is 10 by 24. So probability of 2 stop machine is therefore maximum. That is the answer for the second questions. So we find out the individual probabilities and then we compare the values and then find out which probability is maximum. With this, we close today's session on probability. The probability chapter is very tricky, and therefore one has to really solve many problems. So you must read the theory part and try to understand, and then actually practice many problems. The more problems you will solve, the more you will learn, and you will develop a competency and expertise also gradually. Okay, so let us close today's session. Thank you.